give everyone a minute to get set up. All right. If everyone's ready, we can get started. Yeah.
Yes.
Welcome to today's webinar by the Danish Sound Cluster. The topic today is multi-sensory processing, and we have 3 excellent speakers for you. Yeah, before we jump in, we can just go through some of the practicalities. There's a regular chat, so in there you can write, you can let us know if the sound is bad or if you have general comments. But if you have a question for the speakers, then please write it in the Q&A chat, and then we can handle the questions as they come in a little bit easier. Yes, and our first speaker today is Claire Richards. She is part of the way through her PhD, which is supported by Earcam and Actronica. And Actronica is a company who does high definition haptics. So I think we're going to hear a little bit more about that. What's interesting about Claire is that unlike our network of sort of audio nerds and people with an audio background, she has a design background. And she was inspired by her own hearing impairment to start working with audio and audio haptics. So thank you so much for being here today. And yeah, it's we're looking forward to hearing about your work.
Thank you so much. I'm going to go ahead and share my screen. All right, it is this one. And can everyone see a full presentation on their screen? It's good?
I can see the menu at the top.
You can see the menu at the top. Let me put it. That is one thing. Sorry about that. I'm going to share a different screen then.
Yeah, I think when you shared it before, it was also much bigger and wider.
Oh, okay, that's strange. I have a solution, which is to put this here, make that full screen, and then share this. What about now?
Much better.
Okay.
You can still see the menu at the top, but the whole presentation is much bigger.
Okay.
You might have to put it into full screen still.
Sorry about that.
No worries. Take your time.
What? Well, if it doesn't bother you, I'm just gonna go because
it's great. I can read it. I can see everything.
Okay, cool. So hi everybody, my name is Claire Richards. I'm going to be talking to you today about my thesis research titled Designing for Multi-Modal Interactions Between Hearing and Touch. And my thesis is supervised by Nicolas Misdaris, who's the director of the perception and sound design team at Earcam, and Roland Ken, who is my co-director, who is a permanent researcher at the Centre de Recherche en Design, or the Design Research Center at NC, which is a design research lab. And also my thesis is done in coordination with Actronica, a company specializing in vibrotactile technology based in Paris. So my thesis is about bringing together 2 domains of research, one hand in design and the other hand in perception and perceptive sciences. And I'm doing this by working together with these 2 research labs, so the Center for Design Research and the Perception and Sound Design team. And I'm bringing these teams together so that I can study the integration of 2 senses, so hearing and touch. So my thesis is really all about integration. It's not only the senses, but also these 2 worlds of research, which aren't polar opposites, but they don't have a ton of things in common. So it's my job to bring them together. So I'd like to start off by asking a question, a rhetorical question, which is, have you ever thought about which sense you would give up if you had to give one up? And for me, I knew that I would never give up hearing, which is interesting because I'm actually hearing impaired, which has given me special attention to what sound means to me. And so not only sound, but all senses. So I've given thought to the fact that actually there's a common view of our five senses being separate and discrete, but really our senses are all experienced at once. And the brain has a special ability to take all the sensory information that we're perceiving from our environment and to make a cohesive understanding of it. And a term that's interesting is something called multi-modal integration, so a mode is a sense, so multi-sensory, multi-modal. And it's when one sense directly influences the perception of another. And I am particularly interested in the influence of hearing and touch on one another. So my hearing disability, like I said, it made me especially sensitive to sound, but also to the tactile aspect of sound. So I would go to concerts and I would feel the bass in my body. Whenever my siblings were playing piano, I would want to touch it to feel the chords vibrating. I've always had this sensitivity. And vibration is actually what literally connects these two senses. So between 20 and 20,000 hertz, we hear. And between 20 and 500 hertz, we can also feel. So there's this sensory overlap between the two senses where with one type of stimuli, with one type of source, we can stimulate both at the same time. And so there's actually an interesting thing, which is there are some studies that have involved MRI research, so brain imaging research, that show activity in the auditory cortex when people are presented with tactile stimuli. And even more so for people with hearing impairments. So in short, the brain is really flexible and all of our senses work together. So sound is vibration caused by movement. It's perceived through airwaves, which hit our eardrum, which then make the little bones in our ears vibrate, which then cause the fluid in our inner ear to vibrate. But the same type of vibrations can also be transported through other structures, such as your body. Such as your bones and your muscles and your ligaments. So bone conduction is a phenomenon where sound actually bypasses the external and the middle ear to stimulate directly the fluid that's in the cochlea. And it's mostly been studied for hearing impairment applications involved in hearing aid development, for example, but it's also possible for other musculoskeletal structures. This has been studied, and this is what I'm studying. I'm interested in how bone conduction can work when it's transmitted through the spinal column, on the clavicles, the sternum. And bone conduction in hearing is special because it involves contact with the skin. It involves contact with the body. So not like when air is passing, sound is passing through the air, you don't need to touch anything. It just reaches you through the air. Bone conduction, you need to touch the sound. And so the skin's interpretation of those vibrations in the tactile range, so in that range I mentioned before, it's important too, because we have both senses interacting. So my thesis is about this symbiotic relationship, so mutually beneficial, not only between the two senses, but between these two research disciplines. So I mentioned design, but my thesis is an example of something called research by design. And it's something that allows me to center my research process on my own creative methods that allow me to generate my questions and test my hypotheses. So instead of just having a hypothesis, doing an experiment and then confirming or negating that hypothesis, I generate artifacts. I call them artifacts, which are essentially manifestations of my research questions that allow me to explore the sensory experiences that I want to make possible. So these artifacts that I'm going to spend the next few minutes talking to you about allow me to do a few things. They allow me to explore the constraints of ergonomic design, which is centered on the user, on the human body, and how we're perceiving. They allow me to imagine new perceptive experiences, to question their use as experimental material, so being used as experimental devices in my tests, and to be used as a way to explore use cases of my research for my partner company, Electronica. But that's all well and good. I need to actually understand in a controlled condition what these perceptive experiences are through, for example, psychophysical methods, which are rooted in perceptive sciences, like, for example, absolute detection thresholds, which I'll explain in the next slide, and the possible effects of multimodal integration, like I mentioned above. So all of this to address my main research question, which is, in the search for an alternative way to hear beyond air conducted sound, how can I best transmit acoustic and tactile information to the body? So the first artifact is something that I call the single point module. And what does it contain? So it has one actuator, so one of Actronica's vibrotactile actuators, which allows me to send the signal, a force sensor, which allows me to monitor the pressure of the module against the skin, and an accelerometer to monitor the ground truth of the actuator's activity. So here is a photo of the experiment. I worked with 4 individuals, all with normal hearing for this experiment. I tested 7 frequencies from 50 to 4,000 hertz, and I'm asking these participants, do you hear the signal, yes or no? So it's a pretty classic staircase psychophysical method. And what we're interested in is what is the lowest possible signal that people can hear. So we're taking this module, and I'm taking it and I'm putting it on each of these 7 points in the body. So 5 points along the spine, 1 in the clavicle, and 1 on the sternum. The participants are wearing earplugs to block all the external sound. And so what I'm trying to find is essentially a spatial decay curve for the body. So I want to see the farther we get from the listening point, from the source of the sound. Sorry, not the source of the sound. The farther we get from the stall, how does the perception change of the different frequencies? So what this graph shows in the intensity is logarithmic. So there's a huge change between the values that are the smallest and the values that are the largest, just to note. But we see 2 key points. And these 2 key points are that we have an effective cutoff of perception below 4,000 hertz. So at 4,000 hertz, we have extremely high thresholds, basically at 100% for all of the points, except the clavicle, because it's the closest, I guess. And another interesting point that we have is that we have our highest sensitivity in a very specific range, which is between 100 and 440 hertz. And the reason why this is interesting is because that range centers on the peak of tactile sensitivity, which is 250 hertz. So that's where the skin is the most sensitive at picking up vibrations. But I'm asking my participants not if they're feeling something, I'm asking them if they hear something. So this makes us wonder, is there a potential impact of multimodal integration? And another thing is that these low thresholds don't change. Don't change a lot as we change, as we grow in distance from the skull. So moving on, the second artifact is something that I call the multimodal harness. And the reason why we decided to create this harness, there are many reasons. The main is to be able to follow up on the psychophysical experiment that I conducted, and to be able to broaden our creative potential for signal design. So with the harness, we can explore now not just one point of stimulation, but multiple points at the same time. So this can allow us to simultaneously stimulate several points or create audio haptic patterns on the body that I call the spatialization of audio haptic signals on the body. So this gives a lot more creativity, also because it's a co-development. So the object itself was created in co-development with a costume design studio called Les Vertugadins. And it integrates Actronica's 20-channel haptic card, which functions like a multi-channel sound card. So we're able to control each of the actuators independently. And we did an ergonomic study so that it fits many different people, while addressing 2 main constraints: that it needs to come in tight contact with the body to ensure the transmission of the bone conduction signals, but it needs to still be comfortable. So these are kind of contrasting ideas, and we needed to find a way to make it work. And in the end, it's a functioning prototype. So what we did to explore it last summer was a workshop with my co-director, with Roland. And we use a sound design tool, prototyping tool called Max MSP to create a few applications, some prototype applications that allow us to explore what we can do with the harness. So the first one that I will show to you today is called the Body Equalizer tool. And what we can do is allow anybody who wants to use this tool to create essentially their own personal calibration, their own personal equalizer for each point on the body. So they can create different presets based on the 7 frequencies that I had listed before for the psychophysical test. We take those same frequencies and we allow people to change the relative intensities of those frequencies to have more bass in one part of the body, more highs, more mids, depending on the sensory experience that they want. All of this to be able to listen to music. So a big question that we had was, all right, we can't work in 3D space for the time being. We can't make a 3D torso in Max MSP because this tool is for sound design and we didn't have time to program yet a complete 3D design environment with coordinates for each actuator. So instead, what we did is we created preset configurations of how we can display the different spatialized vibrations. So, and they're based on trajectories. So we have 9 channels total. And for example, the first option of the trajectory is the standard configuration, where we're using each channel independently to stimulate each actuator. And then another alternative is the third option, the vertical large, where we can group channels together to align the signal across multiple actuators at the same time. So very simply, what this allows us to do is to route one signal to multiple channels, and we can create unlimited trajectory configurations, which we can then select in our next tool, which is the body spatialization tool, which is another program that we developed during the workshop, where we can select those presets and work with different variables. So we can change the amount of time that the signal spends at each point by working with the top variable, the position. We can change the volume as the signal duration goes on, and we can change the frequency. So with this, we can create signal sensations that feel discrete, that jump, that do saltatory movements along the back. We can create sensations that feel more continuous. And something that was interesting that we found here is that the tactile sensation is decentralized, right? We have receptors all over the body. If someone taps you on the shoulder, you feel it on your shoulder. If someone taps you on your lower back, you feel it on your lower back. But with sound in bone conduction, what we found is that it's mono. So we just have the sensation that it's coming from within, whereas the vibrotactile sensations are dispersed along the body. So something that we're interested in is how can we kind of maybe trick you into thinking that sound is coming from one part of your body, even if you're perceiving it as being mono. So another big part of my thesis is to think about how can I put this to use. And so to do this, I developed some use scenarios. So these are just imaginations of how this could be put to use. So let's say you want to guide your movements. Let's say a choreographer is having difficulty timing her dancer's movements. And so she asks the dancer to wear the harness. And so the harness sends her some timed vibrations that she feels. And so as the vibrations move upwards, she knows to move upwards as well. Or you want a posture correction. A golfer wants to perfect his posture. So he knows that there's one movement where his leg isn't quite right. The harness has a way magically to detect his body's misalignment, sends him an alert in the form of an audio haptic signal. So he recognizes the alert, he corrects his posture, and then he gets another signal saying, all right, you're good. And then he continues putting. And then another scenario could be a breathing exercise. Let's say I want to learn how to meditate, but I need help to focus my breathing. I'm having difficulty connecting with myself. So the harness could help by sending calming sounds and sending vibrations that tell you when to inhale, when to pause, and when to exhale. So these use case scenarios tie into my third and final artifact that I'll talk about today, which is a product that I am developing with Actronica called Rism, which is rhythm with a French accent. And it is all about dealing with product development. And so I initiated this project to encourage my coworkers to integrate my research into the company. And to be able to do this, I did a couple brainstorms to help them ideate and to generate ideas about the form that this object may take. And this is the form that came from those brainstorms. So the goal is to respond to the immediate business interests of Electronica, because my thesis is done in partnership so that I can bring them interesting use cases based on my research. So what's interesting is that, so I'm working with design studies, and sometimes in design studies, you can operate in an idealized world. But what this project allows me to do is to put my design practice to use and to work with real life constraints. So I'm working as a project manager, and I'm delegating tasks about mechanical engineering, and I'm also helping my colleagues to lead experiments, sort of like the ones I already led, so that we can better understand how each iteration of the device improves as time goes on. So to sum up, the Rism product will be a bone conduction listening device with tactile sound enhancement. We are looking to target audiophiles, but also a full range of hearing profiles, because bone conduction can assist certain hearing profiles given the characteristics of that person's hearing. And tactile stimulation is accessible to all. So this would also be an interesting product for a normal hearing profile. And the use cases that we're targeting are mostly concerning the music experience, but also about self-care and relaxation, such as the breathing exercise use case that I mentioned before. So that's all today. This is my thesis mascot. Listen with your body. Thank you for your attention.
Thank you so much, Claire.
Yeah.
Let me just adjust the view here. Do we have any questions from the audience or indeed from our other panel members? I have a question for you. Well, a few. I don't know so much about bone conduction technology and how it's perceived in the body, but I have worked with car audio systems where we use a shaker under the seat because the car engine masks so much of the low frequency sound that you don't perceive that much bass. So one way to get the direct sensation of low bass is through the seat. And I can say it really enhances the whole listening experience. But when I was thinking about that, I was wondering, you mentioned it was artifact 2. Yeah, you can change the duration of a sound, or the duration. Is that like depending on the frequency, the perceived duration of the note will change?
Yeah, so I just mentioned duration. So duration is one of the, thank you for your question also. Duration is one of the variables just in this design environment that we made for ourselves. And all I mean by that is you can change how long the signal stays at one point.
I see. Before it moves to another. Okay.
Before it moves to another point.
Okay, I think my question is actually, is the audibility threshold dependent on the duration of the sound itself?
That's a good question. I'm not sure I could answer it. I
was just thinking that maybe when we're less sensitive towards 4K, can people hear it when the sound is? Can they hear it more easily when the sound is longer? Jeremy is raising his hand.
That's a really good question. I think. Yeah. Do
you have an idea, Jeremy?
No, but I have a question.
You have a question? Okay, go ahead.
But I think Thorsten has raised his hand before me.
Oh. We have an attendee with a raised hand. One moment, Thorsten, I can unmute your microphone. Oh, can I allow to talk? Thorsten?
Can you hear me?
There? We can hear you.
Okay, thank you. Yeah, Claire, thanks a lot for this nice presentation. Just a question related to, I'm Thorsten Dorf from DTU Denmark. Regarding the spatial integration, so if you have, let's say, these sensors at different positions at the back and shoulder and so forth, and let's say you just to be simple to present the same frequency, let's say 200 hertz or something at different positions. how is this information integrated? So does it add up? Is there spatial integration also that I don't know, that if you have 5 sensors that you need lower kind of vibration amplitude to hear it essentially, or how is that spatial integration? Is there any spatial integration, or is it just independent?
Okay, so yeah, thank you for your question. I think, so if I've understood correctly, what you're asking is if you're sending the same stimulus to multiple points at once, do you have an amplified perception as opposed to just
does it integrate? Is it integrated across?
Does it feel louder? Like, is it like an addition of the 3? I mean, that's a super interesting question. My first response would be to say that, well, we first have to kind of separate the way, like, tactile versus auditory perception. Because so we're not going to perceive the same stimulus the same way, more so in terms of bone conduction than in tactile perception on different parts of the body. Because from what I have learned, the farther you go from the skull, the higher your thresholds are, except, like I said before, except for that certain range of frequencies. So it's kind of a loaded question because your tactile sense, maybe you would have an addition, a summation of those sensations because you have multiple points stimulated at once. But for acoustic, that's a good question.
Yeah. Okay. Thank you. Probably not, because you said you of course, if you can easily localize. I mean, this the kind of sensation, but probably it's, I don't know, because you talk about the connection, helping hearing via vibration. So I don't know if there's, so to speak, if it helps to have the same stimulus from different positions. But I don't know. But thank you very much for your answer.
Thank you.
Yes. So I have a couple of questions. So first, and we talked about this before, is in your first experiment when you have this threshold, you mentioned that you asked people to tell you if they heard the signal, but it's quite difficult to know whether they heard it or they felt it.
Mm-hmm.
How do you make sure of that, or do you need to disentangle that?
So so thank you for asking this question, because this is something that I spent a lot of time thinking about before designing this experiment. Because we know that for some frequencies there will also be a feeling component to the sensation, but we chose to not ask 2 questions or 3 questions. Did you hear it? Did you feel it? Did you hear it and feel it? And just to ask, did you hear it? And to let the participant, to leave them to their own devices, essentially, to say, am I feeling or am I hearing this? Like, there was some confusion sometimes, but what they are supposed to be answering is if they heard it. So hopefully that's what's going on. When they are saying yes, they're actually thinking, yeah, I heard that. But so it leaves some confusion as to thinking, is it going on at an conscious or an unconscious level, the confusion between am I feeling or am I hearing? Like, am I really thinking I'm hearing it and I'm saying yes, or am I saying yes because I'm sensing something? Is that kind of yeah.
Yeah, but somehow if they say yes, I heard it, and if they're confused, maybe it's also somehow
Maybe that's
a good
also
thing.
interesting. Yeah, exactly.
That's interesting. But maybe you did not try to add some purely audio sound through headphones to try to confuse, to trick them. Say, was it audio or was it? But maybe the sound quality will be different. Can you reproduce the same quality that they will hear? If it's just a pure tone, you should be.
Yeah, that should be possible. Yeah.
Okay.
It's something we haven't done yet. But yeah.
Okay. But maybe if you have it on different side, you should hear it more into one ear rather than the other. So you can have some.
Oh, sorry.
You can have some localization task where they have to point it, stuff like that. That could be fun to do. And so in your harness, you also wanted to create some different sounds, but the main goal was also to really make sound that they could hear, also feel somehow?
So that's a good question too. So we have both goals, and they're happening differently in the different applications that we made during the workshop. So in this first application, the goal was more to focus on, all right, how much can we hear out of a given sound sample compared to how we would hear it in headphones. And what's really interesting is that there was actually one person who said that he heard it as if he were hearing it in headphones when only the very bottom of the back was being stimulated. And then there were other people who were saying, like, this is totally pointless. I can't hear anything. So we have some variability between people that could be due to different morphologies. And so, yeah, we can address both questions. But yeah, so for this application, it was more about what are we hearing? And for this application, we're thinking more about the tactile sensations that are moving across the body and how we can kind of trick you into thinking that it's not just the tactile sensation, it's also the sound that's traveling across your body.
Thank you.
We have a question from Hamish. I'm just gonna.
Hi, can you hear me?
Yeah.
Yes, we can.
Hi, it's Hamish. I'm from Ericsholm Research Centre, also in Denmark. Thanks for your super interesting presentation. I really like this design approach. I think that's cool. I was wondering about the biomechanics of this bone conduction from so far away from the cochlea. I'd never thought that sound waves could actually propagate that far through your body. And then Jeremy also asked the question that I was going to ask about are you just feeling it? And one thing I wondered, maybe this is something for someone else to do sometime or you to do later, but I think there are some kind of contact microphones that are used in diagnostics, hearing diagnostics for bone conduction hearing, where they put contact microphones on the forehead or somewhere on the head to actually measure the output of the bone conduction device through the bone. So you could actually figure out if you did something similar by putting your bone conduction devices down on the lower spine and see how much actually gets up to the head. That could be interesting. So yeah, that's maybe.
Oh, you cut out.
We lost Hamish.
Yeah.
Yeah, I cut out. Maybe that was the end of his question. We have one more here from.
Maybe more a comment than a question, but anyway.
Oh, he's back. Sorry, Hamish, you were cutting in and out there.
No, I think that's the end. I've got a bad internet connection, so I'll just be quiet now.
Okay, well, I heard you. I think I heard most of it. Thank you. Yeah.
Thanks a lot. So this question is from A.T. Christensen. Is the single point module in artifact number 1 somehow calibrated across frequency? If so, do the thresholds follow average bone conduction thresholds measured the standard way?
Yeah, okay, so that's a really good question. So the calibration, I think that he or she, I didn't catch the name actually.
We don't know, it's AT.
Oh, okay. The calibration that they are talking about is what we were actually looking to study. So the module itself isn't calibrated. We were using the module to try to come up with an estimation of calibration for signal transmission across these specific frequencies. And the second part of the question was, sorry.
Sorry, the second part, if so, do the thresholds follow average bone conduction
Oh,
thresholds?
yes, of course. Okay, yeah, so that's the interesting part. So what we are doing to follow up this study, what we're currently doing is using the same module with different signal resolution settings, because the thresholds are so much higher on the body compared to the skull, so we've changed some of the settings. But we're going to be doing the same study on the skull with the same module so that we can make a comparison to the literature with those with the bone conduction thresholds that exist currently, which are mostly taken on the mastoid, which is the part right behind your ear here. So yes, that is completely relevant.
Great, thanks a lot. I don't think there are any more questions for now. So if anyone has more questions, you can type them in, and Claire can either answer you via text, or we'll try and take them at the end if we have more time. So yeah, thanks a lot, Claire. That was really interesting. Let's move on to our second speaker for today. That is Jeremy Marrozzo. He's the leader of the Music and Cochlear Lab at the Department of Health Tech at DTU. And he also spent some time at IRCAM. That's where he did his PhD. And as well as that, he's been working around the globe. Let me see the list here. Marseille, Boston, Melbourne, Switzerland, and primarily working on research to do with music perception for cochlear implant users. So yeah, as we heard from Claire, we are perceiving music not just through the ears, but also through vibrations, and hearing impaired listeners rely more heavily on this to compensate for their deficit. And this is what Jeremy's working with in their lab. So we're going to hear about some of the different projects that he is currently working on. Thanks very much for being here, Jeremy. We cannot hear you, but your slides are looking good.
Okay, good. Is that better now?
Yeah, that's great. And we need yeah, if you just go into presenter mode.
Yes. Okay.
Then all will be well.
Is that here? Now you get
Perfect.
it? Okay, good. So thank you, Shelley, for this opportunity to present some of the work that I've been doing with my colleague at the Hearing System group at DTU. So this project, we're focusing, it's what we call augmented hearing. And the main aim of this project is really to restore the musical experience for hearing impaired listeners by conveying low and high level musical feature through cross-modal enhancement. So that's a mouthful, there's a lot of different words. I think one of them that is important, and I will start by trying to define that, is what I mean by cross-modal enhancement, because it's using tactile device to try to restore hearing in hearing impaired listeners is not a new idea. In fact, it's very old. However, there's no big product in the market that's working so nicely. So we try to understand why, and we try to come up with a better approach. So when we talked about how we perceive the world through all the different senses, we know that we often associate one modality with one sense, like hearing and the auditory system. However, we know that we perceive it, and as Claire beautifully said, that we perceive the world through all modality, and they all combine for the different senses. And combining modality can be done in different ways. And in neuroscience, they define it two different ways to integrate that. One is called multi-modal integration, and the other one cross-modal enhancement. So the multi-modal integration is when the perception of the sense is composed of multiple modality that is integrated, but they don't really combine. It's just you're taking all this information together to get a better kind of understanding of the world around you. So one of the example is if you listen to, if you're watching for me, I don't speak Korean, but if I'm looking at a Korean movie and I get the subtitle, I have one modality, which is the audition, and one other modality, which is the subtitle, the visual part. And I'm taking both modality to have this experience of the film. However, I've been in Denmark for a long time, but despite that, my Danish is still very poor. And when I'm watching a series of a Danish movie with the Danish subtitle, by reading the subtitle, that will transform the way I perceive sound. And that's what we'll call cross-modal enhancement, is when one modality influences the other modality. So to illustrate that, I have a little demo that I will try. So first, you're going to listen to a sound that it's just from a movie, from a South Korean movie.
우리 동네에선 그 노래를 오징어라고 불렀다. 마치 오징어를 닮은 그림 때문에 붙은 이름이었다.
So unless you speak Korean, you should not be able to understand anything. Now I'm going to play you another audio example where it's the English version, so exactly the same thing but said in English, so you should be able to understand. However, to make things a bit harder for you, I've passed this through vocoder to degrade the sound, so to degrade your auditory modality. And again, unless you're very experienced to listen through vocoder, you should not be able to understand anything. Now, what I'm going to do is I'm going to add the subtitle. So here's the subtitle. And you're going to listen again to the Korean sound with reading the subtitle.
우리 동네에선 그 노래를 오징어라고 불렀다. 마치 오징어를 닮은 그림 때문에 붙은 이름이었다.
You can now listen to the English version that is not vocoded, reading this. So here, what I mean is that now you get both modality, but it was even hard to associate different words to different sound. So now if you listen to the English version with the subtitle.
In my town, we had a game called the Squid Game. We called it that because it's played in a court shaped like a squid.
Here, because the audio is so good, the subtitle doesn't really bring anything. Okay, you get all the information through the audio. Now we're going to listen again to the vocoder, but try to listen to the vocoder while reading it. So hopefully we spent about 5 minutes listening to this. I hope the demo worked. So the last time I could not see your face, so I'm just hoping that it worked really well. What you should have experienced is the audio would have been modified by what you saw. But again, if the audio was too precise, the visual will not modify it. So this is kind of a sweet spot where the auditory modality needs to be degraded enough really to benefit from the additional modality. So that's why everyone thinks, oh, well, let's try to do some audio tactile thing to compensate, or at least to bring this additional modality for hearing impaired people. And in fact, when you go to a concert, you can feel the vibration, like Claire was saying, or at least she likes to feel the vibration. There's also a lot of hearing impaired people that will go to a concert with big balloons just to enhance the vibration. And there's heaps of commercial product. Some of them are more designed for gamers, like this vest here and here, or some of them are more designed as a sound awareness, or even a tinnitus treatment. And not only those devices exist, but already if you go to a nightclub that is designed specifically for deaf people, you have already the solution. So here's kind of a nightclub where you have a DJ here, and the sound, the PA will be connected to different tactile that will be placed below this floor that will vibrate. So the deaf people could come and feel the music. It's also fun that you can see here, there's this big fan here with smell. It's actually a smell jockey, which will produce a smell that should align with the music. So if those devices are working, maybe there's nothing else that we need to do. We just need to kind of convey the music, and they need to touch loudspeakers, and our work is done. That's a bit what we started. However, we thought that if they can enjoy music through that, what kind of musical cues or what part of the musical signal are they really relying on in order to enhance their experience of music? And that led us to our first question, which was what part of the musical signal should we convey? Because if we want to build a system, maybe if we don't have to bother with different type of musical cues, it will be more efficient. And this question was answered by Scott Acker, our PhD student that's doing his PhD on this topic. So you can see here the picture of Scott actually try to think why he's studied his PhD and not a job well paid. So in this first experiment, he has presented to people a musical signal that he has decomposed in different musical cues like pitch, intensity, and rhythm. And he has showed this musical sample through headphones, but also through tactile. People were holding a little device that was vibrating. And in the first condition, the tactile input had the same cues as the audio one. So there was a kind of redundancy of information. In the second condition, the tactile device had the same intensity and same timing as the audio, but he randomized the frequency. So if people like better this combination, audio with the tactile signal compared to audio with the tactile signal and the frequency randomized, it will mean that the frequencies cues is important. In the third condition, he randomized the intensity. Here again, we can compare between the tactile with all the different cues and the tactile where the intensity is randomized. In the third condition, he randomized both the intensity and the frequency, and in the last one, he randomized everything. And each time he asked people to rate how well they perceive the music or how well they enjoy their musical experience. So here's the result. You can see here the rating from 0 to, yeah, I enjoyed it a lot. And here are the different conditions. So when the tactile was exactly the same as the audio, the rating was quite high. So it means that, yeah, you can provide some feedback that will kind of enhance the musical experience. On the other hand, when everything was randomized, so the tactile one was kind of it was just shaking everywhere, people really didn't like it. And this condition was important because we wanted to know whether just holding something that vibrates can enhance your quality of the musical experience. But what is interesting now is if you're comparing this condition where the tactile one was totally in sync with the audio and the tactile stimuli where we randomized the frequency. And you can see that although the variability is much bigger in this second condition, can you see my mouse here? In this second condition here, it was not statistically significant. So basically, by randomizing the frequency, you don't really impair this tactile signal. However, when we randomize the intensity, the rating goes way down here, showing that the intensity is a very important cue in order to have a good experience of audio tactile music. And when you randomize both the frequency and the intensity, it's also not significantly different from when you just randomize the intensity. So again, randomization of the frequency doesn't seem to have any effect. Although he has, Scott will tell you more, he has some additional condition where you could find in some condition that the frequency mattered, but it was way less than the intensity. The second question is, can the auditory perception be modified by the tactile input? So here is going to, again, to this question of cross-modal enhancement. So can really, can our perception of sound be modified by the tactile input? And that was the subject of the master project of Tushar Verma. And he studied specifically timbre. So his question was, can we modify the perception of timbre through the tactile sense? And he has created 6 different stimuli that vary both in terms of attack time, so even with a sharp attack or low attack. So the one with the sharp attack will be perceived as more impulsive than the one with the shallow attack. And those stimuli also had 2 different amplitude modulation depth, from low amplitude modulation depth that sounds smooth to a high amplitude modulation depth that will induce a sound that will be perceived as very rough. So those 6 stimuli were presented through headphones, but also through a tactile device that people were holding. But the funny thing is that we kind of mixed up the audio and the tactile. So sometimes we could send an audio signal that is very rough with the tactile signal that will be very smooth, or vice versa, or a tactile signal that was with a very shallow attack with an audio signal with a very sharp attack. And we wanted to know, and we specifically asked people to rate only the audio part, to kind of ignore the tactile part. And we wanted to know if they could do that, or whether the tactile input could affect the way they would judge the audio signal. So here is the result. So where we can judge how people have judged the impulsiveness of the sound on this axis here. And here is is how we can predict this judgment. So to predict this judgment, we had to do a linear combination between the audio attack time and the tactile attack time. So I don't want to go too much into details, but the bottom line is that in this experiment, we found that our perception of impulsiveness was influenced at 88% by the audio signal and 12% by the tactile signal. So that's kind of this red line here. That's the magnitude of change caused by the tactile input. In terms of roughness, here you have the roughness judgment compared to our model that is based on 75% of the audio and 25% of the tactile. So here again, we can the same signal was judged as the same audio signal was judged as more rough if they were holding a tactile device that was more rough. So basically, we influence the way they perceive the roughness here. So this experiment worked well. We were happy about that, but we thought this is a bit small. Maybe we can induce a bigger change. And maybe this change is quite small because they're just holding something in their hand, and it's not very natural, because when we feel the vibration, we just don't feel it in the hand, we feel it in the whole body. So we thought that if we place the tactile in a different way, we might have a bigger effect of the tactile input. And that was part of the master project of Miquel Sierra. And what we wanted to do is to create a structure that will activate different parts of the body in a kind of organic way. So one solution would have been to use a Claire harness, but we went to another solution where we created a bed, pretty much. And our inspiration was from the kalimba, this African instrument, that it's composed of different little metal bars. And each bar is tuned to a specific frequency. So when you struck those bars, you have different notes. However, imagine that you can put a shaker on this kalimba at the very specific resonance frequency of 1 bar. Suddenly, only this bar will vibrate. Now imagine that this kalimba is huge and you can lay on it. It means that with one tactile, you will be able to stimulate different part of the body. And so that's kind of the structure that we designed here, which each of those bars was tuned to a specific frequency. And you can see here the COMSOL simulation that with one given frequency, we can activate this bar or this bar here, the different bars. So all the simulation worked perfectly. So we designed and we built the bed. And you can see here the big frame with all the different bars that it's tuned to a specific frequency. We had to put some big strap on it because we were afraid that once you lay on it, your weight will kind of break the different bars. The structure worked great without anyone on it, but as soon as you get into it, the body, the weight of the body has a lot of interaction, meaning that the resonance frequency of the bars were a bit skewed. So therefore, we had another kind of a project done by 3 students, Brett Risman, Gabriele Ravisa, and Thomas Teschle. And so basically, they built on this kalimba bed. And the idea was to build another structure where, again, you could feel the vibration in a different part of your body, but try to minimize the effect of the body itself. So to do that, they created those 2 big prototypes, those 2 big chairs, which are very heavy. They required a lot of work. So those 3 students done an incredible job here. In this first prototype, they took back the idea of the different bars that will vibrate at different resonance frequencies. And you can see here, those bars were connected to a beam that went thinner and thinner to reproduce a little bit like the basilar membrane shape, where depending on the frequency, different bars will be excited. They also had some different dial here that will vibrate at different places. And they built another chair. So this one was nice, but it was a bit difficult to get in and out. So we thought maybe if we just excite the structure, that will be enough. And that's this second chair here. And in this one, you have 3 tactile, 1 here for the leg, 1 here for the butt, and you have here 1 in the back that you cannot see. So I'm going to show you a little movie during where we tested that during the integration. I don't know if the movie Okay, so I hope that the video was smooth enough. So now those 2 chairs has just been shipped to Geneva because we have a collaboration with the museum and 2 Swiss artists to create an audio tactile installation to enhance musical experience for people with an handicap. So this collaboration has started already in October last year, where with the 2 artists we took a different podium and we put some tactile into it, and we placed that in the middle of the museum where we invite people to be able to experience. Here there's a musician, a live concert while feeling the vibration along the body. This first installation worked so well that the museum asked us to do something that would be more permanent over the whole year in 2022. So in this, the idea with this project in collaboration with them is that every month in 2022 there will be a concert, and using those prototypes, so the podium, but also the 2 chairs that we're going to create, and based on the feedback of the audience, we will build a new prototype that we will send, 1 in March, 1 in July, and 1 in November. So it's an art installation that is evolutive because based on the feedback of the audience, we kind of improve it constantly. So that's it for my little overview of the different research topic. I'm happy to take any questions. Otherwise, you can always send me an email.
Thank you very much, Jeremy. We will certainly share your contact information with everyone here. So if you want to reach out, you can do so afterwards. Does anyone have any questions? Perhaps from our panel? Oh, we have one here in the Q&A. Yes, one from Sina Thompson. Are some kinds of music more suited for your experiment?
Yes. So we only. Yes, that's a very good question. So, and also that's where the collaboration with the musician is priceless, basically, because we often come with engineering state of mind and we want to control everything. And we were building those devices, but I thought if we give those devices to musicians, they'll be the one that will come up with the different type of music that will be the most suited. So already by working with them, we kind of figure out that we can use some rock song with heavy bass, and everything will be shaking, and that will be fun. But beside being shaking in everywhere, that doesn't bring so much a greater experience. It's fun, but it's not enhanced somehow. And when the musicians try that, they told us right away, oh no, everything is way too loud. You put way too much vibration. And they started exploring different type of music, and they came up with this gong thing using Tibetan bowls, because there's some very kind of quiet low frequency and also some very distinguished frequency, like the higher frequencies. And when you experience that, you can hear the different pitch going into different places, but also you can localize it, even though it's always the same. The tactile is always in the same place. You can really localize it in different places on the chair. So that's I will say music with some distinguished frequencies, but also not too much happening. So you can really associate the different instrument with the different type of frequency.
I can imagine it would work best without too much. I mean, rhythm is nice, but without too many crazy drums.
It's nice, but it's obvious. It's like I mean, if you're putting a techno music, it's like reading the subtitle with the English version. You already hear it, kind of, or you already kind of. It's already there.
Yeah.
It's more interesting when it's something that is not there so way. So.
Yeah, and these kind of sounds that we just heard, and like the Tibetan singing bowls, are already used in sound healing and sound baths, I think they call them, as well. So it would make sense that they would also work well. Do you know, like the musicians you were working with? Would they also working together with hearing impaired listeners?
They start through our collaboration. So I present them with hearing impaired listeners. They are also very sensitive to working with handicap in general. So in this installation in museum, it's really more the inclusive art scene. So we try to include everyone. So we designed that in mind with the hearing impaired, but also it works with other type of handicap, I may say. People that are not so used to kind of experience music, to have something that is a bit more physical also could be helpful somehow.
Yeah, definitely. So interesting. We have another question from the audience here. The audience at the museum were people with different handicaps. Oh, which type of handicaps were these, and were some of them more receptive for the experiment than others?
So far, yeah. So we just had one. I mean, we will hope to be able to answer that next year, because the first one in October we tried to collect some data, but it was done a bit in a rush. So talking with, and I couldn't be there during the concert because it was COVID. Based on what the musician said, all type of handicap worked well. I'm not quite sure. I hope that I will be able to answer your question next year.
Yeah, you should definitely come back whenever they've had all of the different models and yeah. When was the last one? November 2022.
Yeah.
Okay, we'll have an update then.
Okay,
next
great.
1 year from now.
Yes.
Thank you very much, Jeremy. I think that's all we have time for at the moment.
Okay. Oh, yeah. Cool.
Yeah.
Yeah. Good.
Then we'll move on to Shumhua, and of course, if anyone wants to contact Jeremy, you can do so. And we'll hear from him in 1 year from now. Anyways, thanks very much for presenting. So our third speaker for today is Shumhua Eckhout. He is an associate professor at the University of Aalborg in Copenhagen, and he works out of the Multisensory Experience Lab together with a lot of people, but Stefania Serafin, who has been on one of our recent webinars as well. So great to have another member of the lab here. His focus is on sonic and embodied interaction design, audio signal processing, and physics-based deep learning. And prior to coming to Copenhagen, I think that was in maybe 2014, he got his PhD from the Technical University in Helsinki, and then completed a number of national and international postdoc research projects as well. So you've been working in this field for a long time, and we're very happy to have you here today. Thanks a lot.
Thank you, Shelley. Do you hear me fine?
Oh, yes, I can hear you fine.
Sure. Then let me share my slides. And while doing that, I should say how happy I feel my embodied interaction part feels to see research through design, making artifacts and evaluating, going side by side with scientific inquiry. I think that's what we've been fighting for so many years in the Sonic Interaction Design project. Now it's a reality, and we do a lot of stuff like this too. So this is great. But what I would like to talk today is slightly different. It is about what we've been doing in the Multisensory Experience Lab in the past years and what we'll aim to do in the future. So let me go to the full screen with presentation. Does everything look good?
Looks great.
Good. Then if you don't have time, or will you return to this presentation later on, this is all I have to say. The rest is arguments for that. There are 4 links. One of them is our lab, Multisensory Experience Labs web page, where you would find lots of ongoing projects and publications and demonstrations. The second is my curated list of publications, which I always tune to a particular event. The third in the middle is geometric deep learning.com and physics-based deep learning.com, and that's what we think which has some directions which will have a lot of impact in our research and probably your research and your companies too. So that's everything in a single slide, and where we're coming and where we're going through as well. But let me put a bit more substance to that by going deeper into the field. So we started to develop a vision of sound and music computing circa 2012-13, when we finished several of the European projects we talked about. And that was also the year to 2013, I joined Aalborg University in 2012, where we made the first summer school on product sound design in Copenhagen. And we also moved to Nokia's LX facilities in Copenhagen. And this is the same slide that I showed when I was invited to Danish Sound Network, then not a cluster, annual talk about what we're going to do in the future. And we said that we will be looking at the virtual reality. There wasn't Oculus, or there wasn't any kind of a big affordable frameworks. And we can do that well because we're coming from a model-based modeling background, and we look at the interactions, multisensory interactions. That was our vision, to combine, to put the focus into the interaction. And we said that we're going to do some musical instruments with that, and we're going to try to understand the music from the multisensory point of view. And if you look at about now, I think under Stefania and Rolf's leadership, we've been, in my opinion, quite steady in this vision, and we formed the Nordic SMC network. And we are doing a lot of projects again in the virtual reality with still models, and all our PhDs are bringing new problems and interesting domains. So let's start from here then. I'm going to show two projects. There will be videos, but I'm not going to use the sound. So if you're interested in the sound, you can watch later on. There are some points I try to make with them. The first project is from Sylvain Willemsen, and it's a audio haptic virtual reality installation that you can play a bowstring instruments, in that case trombone marina. So the idea is to make a physical model out of the instruments, and since the model is physical, the haptic input, the coming from phantom device, can be also put to the model, and the visual modality also supports everything behind this. So you can, in the virtual reality, play, and wherever you touch, you get different sounds. Just with a sound closed, a basic walkthrough is, this is maybe what you see in the virtual reality, and you can change the bowing point and you get feedback about the instrument. You hear everything in real time. And that was part of Stephen's PhD thesis, supervised with Stefania. And this is one of the experiments. And there have been many virtual reality musical instruments, and we made some papers about that, and we've been following this path quite reliably. And after that, I'm going to go to another project, now provided by us, Camilla, who is making an industrial PhD with a Danish creative industry company called Macropole. And this is 2019. We invited Macropole and friends for a workshop at Multisensory Experience Lab. And we used two motion capture suites, 64-channel wavefield synthesis, and what else? Also IR tracking, but we didn't use in that. In the same thing. So please do think about the throughput of real-time data, and we're doing that in audio rate. So there is about 100 channels of data coming. And then what we do is we're making machine learning in almost real time on this data to understand and create virtual characters, meanwhile modulate the sound. So there are interviews and there are quite interesting video, but I'm not going to play it fully. Here are two sound designers working with the motion data and directly mapping everything to 64-channel wavefield synthesis. And here the environment space. And here is the motion capture part. There's a choreographer and an experiencer. This is an experience for a single person who is wearing the virtual reality thing. And what we do is we analyze the movements of both participants and generate real-time avatar characters, which are modulating the sound as well. So, and there's a narrative. Everything is driven by the narrative of singularity, that this artificial intelligence creation would slightly start with mimicking the humans and then find its own way and try to a bit deteriorate for what we do. So at the end, all these agents will be merged into self-determining environment. The reason that I put these projects, there can be many others, is by this amount of data and looking at this specific data, we started to realize some interesting things about our usage of data and about the models that we're using. So there are multisensory experiences. In the first case, it's audio haptic. In the second case, perception, the inertial sensors movement is coupled to sound and vision. And we're getting some kind of data which we record, consume, and analyze in real time. And it is idiosyncratic data that we can avoid big data and all its problems like measurement bias, representation bias. We're getting the data and consuming, and the way we do that is in models. And that realization is important because first it relates to the responsible data properties now, but most importantly, the focus on the model affords very interesting directions to go in the future. And this is what I want to emphasize in that talks. So let's go a bit in time. Maybe in around 2000, 20 years ago, we were using such models which are made for digital signal processing components. Also, even in the virtual reality, and we had tools also for calibrating the model parameters from the data. But nowadays, we can run them in real time, put in the virtual reality, and the analysis tools are coming more and more to the field of our research. So this is a publication that I made with Finnish colleagues 20 years ago, and I see lots of them in the audience list as well. Hi, Terveisiä to everybody over there. The core calibrator was what Jeremy mentioned as well, essentially a vocoder that was analyzing the sound, and we had some optimization routines to, so to say, change the parameters of the vocoder in real time. That's what we do in 20 years ago too. But a disturbing thing then and now was there was a mysterious entity in the model. So we knew what we were doing and how we were doing that, but there was a black box approach which we could not explain. Nonlinear optimization is like that, and most of the deep neural networks are like that too currently. The breakthrough in that was when we come from the data and sensor point of view, even the most probabilistic models become that we can understand that, explainable AI. Here's an example about simple word thing. We regard the whole sentence creation as a field of tree of possibilities. It's not too far away from the trees that we use in physical modeling sound or the scene graphs in the virtual reality too. So another example of handwriting generation, these models are typical deep learning models, but when you look from the particular angle, you see a dynamic tree which is forming and modulating its parameters in the real time. So what happened recently is we also find a way coming from Google's research, but not only from there, from different points of view, to have differentiatable machine learning models. Differentiatable machine learning models mean that we have strong inductive biases and we keep the model structure intact. So if you're using a vocoder, the learned model is still a vocoder. If there's a graphical tree, it is still a graphical tree. We know what is happening there and we can analyze. With that thing, I'm going to show maybe the last one. This is one of our current research. By that, we first focus on sound synthesis. So here's a differentiable 4-operator FM synthesis, typical in Yamaha DX7 synthesizers. And by learning the parameters and putting them into the latent space, we have a very good understanding about how sophisticated sound algorithm works. And Jeremy would know that because it was a master thesis that he evaluated as well. So with that, we are now with the focus on our own generative idiosyncratic data, multi-channel sensor data, and differentiatable machine learning models. Now we're in a level to set a vision to what's going to be in the future. And we call that differentiatable sound and music computing. And we very much hope to put that framework in the 10 years. Interesting capabilities of that is there's so much to talk about that, but so little time on this. But the most interesting capabilities is since the models are differentiable, we can use the DSP models or any kind of machine techniques we're familiar with, only we understand where to shift attention and how to infer the outside model to create interesting solutions with that. One approach could be looking at the hearing aids. Now, I think we know the acoustical pathway. Do you see my mouse, by the way? I don't know if you see it. I can make it bigger.
Yes,
Thank
see
you.
it.
The blue is the typical ear channel, and then we have the bone conduction, and the researchers are now looking at another path, cartilage conduction, by following the idea of Nishimura and Hosai. So when we look at this, there's a physical model involved with that. So we can take these physical models. This is not too far away from all the synthesizers model that we have, or some dynamical trees that we do in virtual reality. Then we could not only have an output-input mapping to the model, but keep the model and experiment with the parameters. So that would allow us to cultivate some kind of models which are optimized by gradient descent, and we can understand the situation under question much better using this approach. So these are our vision. Basically, we came from the physical modeling, model-based synthesis, first in sound, then in virtual reality, and we like this research line. And I think there are lots of laboratories now are also founding or building this kind of things. We like it, but we also want to extend to modern approach in deep learning, which won't involve only a black box mapping, but will give us more structure. And we're looking especially into the direction of graphical machine learning and physics-based deep learning. They are funded by ERC, so they're very nice material behind this. And we would be happy if some of you would be interested to join us in that environment, in that endeavor, and that we can look at that together as well. So this is all I want to say. This is my single slide, last slide, and this is our vision for the future. By differentiable physics-based learning models, we try to address the dynamic movement and seeing graphs with responsible and idiosyncratic real-time data and explainable machine learning. So now I stop here and stop sharing as well, unless somebody wants to see some of the material once more, and would be happy to hear your questions and comments.
Thank you very much. That was very interesting to hear about your project and also your vision. If in a dream scenario, which kind of companies would you like to partner up with?
Any company who are using some specified model they want to test and they want to put. Moreover, we had lots of investment on deep learning in Denmark, as you know, and of course we expect that there will be a little bit of variance. Not only black box model will be funded, but also explainable and physics-based model will be funded. We're interested to look at that direction too. And just to give you an industrial thing, the proponents of the differentiable programming and everything are at the moment running, for example, Tesla. Andrew Karpathy is the head in the Tesla R&D. And Jan LeCun also said very wonderful things about the idea. So I think industrial involvement will be everywhere very, very strong. And we hope to also do things within our friendship networks in Denmark.
Excellent. Maybe I should take a moment to mention that we are able to fund some projects from the Danish Sound Cluster, and that's a collaboration between a university or knowledge institution and 2 other companies. And we're able to pay the university salary for that kind of project. So perhaps there's some potential partners out there for you. Do we have any other questions? Jeremy and Claire, do you have any questions for Shumhua?
I did have one question. It was about the Tromba Marina.
Mm-hmm.
I was just wondering about the haptics part. Was it just force feedback, or was there also a vibrotactile component?
Stefani is online. She's conducting this search. Should we connect to her, or I mean, as far as I know, Oh, Stefani is there already.
Here she is. We can hear her.
Hello.
Hi.
Hi. Thanks for the very nice presentation, everybody. There was also a vibro-tactile component. And that is also, we made a more thorough experiment with the guitar string, actually comparing the Falcon device with that one augmented with vibro-tactile or just with vibro-tactile to see which one recreated a better tactile sensation of playing a guitar string.
Okay, thank you.
It was, as expected, the combination of the two.
Yeah. Okay.
I participated as a performer in the test, so I know the sensations, but I think we should hear that from the research organizers.
And what was your experience?
To play the trombone marina.
Yeah, did it feel like playing an instrument?
Well, I think in virtual reality, when you create sound, there's a certain pleasure involved in that, being active in that environment, and whatever you play sounds good. But when you listen to what you played afterwards, it sounds terrible. So my experience during the thing was great, but when I heard anything about that, that was not that great. That's because of me, not the model. As a performer, I just don't know.
I see. If we don't have more questions, then perhaps we have one more question for Claire and Jeremy. That's all right. From Vidya, there's evidence that sensory deprivation over time leads to cortical cross-modal reorganization. How might that impact your results regarding auditory and or tactical sensitivity?
Should I start, or you want to start, Claire?
You can go ahead. Yeah.
So that's a very good question. Interestingly, some of the research, we always think, oh, if someone is deaf, it should be way more accurate in the tactile modality. But the first research that I could see is not the case. Deaf people are not better in discriminating frequency. However, they might put more weight into that modality. So when you have an audio tactile stimuli, and that's the research we have done with cochlear implant users that I haven't presented, there's a very big differences between the result that we get from normal hearing listeners and CI users, because they just integrate way more the tactile sense. So it's always interesting when we're doing this research to do the same testing with people with cochlear implant or people with hearing impairment, because they will have a hugely different result. And one way to simulate that is always to listen to the sound through some type of transformation that will degrade the sound.
I have a question.
Oh, yeah.
Or maybe Claire wanted to add something. No?
Yeah, of course. I just want to know what cortical cross-modal reorganization means before I hear Claire's answer.
It means that if you look, there's some research that show that if someone is totally deaf and you stimulate that person with the tactile sense, the place in the brain that will light up can overlap the auditory sense, the place that is usually attributed to the auditory cortex for normal hearing listeners. So basically, the brain, the real estate is very expensive real estate. So if you don't use a part of your brain, it will be taken over by some other senses.
Okay, that's good to know. Thank you for the explanation.
Mm-hmm. Yeah, I think another term used to say the same exact thing is compensatory plasticity. I've heard that thrown around. Mm-hmm. And yeah, I was just going to add on the question with another question, which is, Jeremy, have you worked with people with hearing impairments that differ based on the age of onset? So like from birth versus later in life, and how has that impacted their ability?
So we did that with CI users, but I don't think we have done that for audio tactile, any audio tactile sense. It's always very difficult to get a good panel of CI users. So we always deal with very small numbers. But that's a very good and interesting question.
Thanks.
I think that's all the questions we have for now. Did you have anything else to say, Shamar?
Oh, thank you.
No? Then we're also out of time. So I think for today, I'll just go ahead and wrap it up. But thank you for all 3 presentations. It was great. And thanks for the questions from our audience today as well. For those who couldn't make it today, we will send the recording out, so you're welcome to share that with perhaps some of your colleagues might be interested in hearing these presentations. And before we go, I would just like to let you know that we have, of course, more wonderful events coming up in January. One of them is multi-channel sound for headphones on the 11th of January. Then we have online services for hearing rehabilitation, so remote care and from some of the Danish hearing aid companies. And we also have sustainable transformation in audio companies on the 25th of January. And finally, a VR workshop at the Multisensory Experience Lab. That is at the end of February. It's not online yet, but it's coming soon. So we'll just get the final details in place before we start promoting that. But that's going to be great. And nice to do a physical face-to-face meeting for once instead of online. So hopefully we'll see you there, Shamor. And yeah, thanks very much for participating, and happy Christmas to everyone if we don't see you before.
Yeah.
Thank you very much.
Bye.
Bye. Have a great
Bye.
evening.
Thanks.